thanks for the introduction. So as you said, I'm in my second year, so I'll probably be around for a little bit. I'm going to talk to you guys today about laboratory investigations of wind-slab interfaces under a controlled temperature gradient. This project kind of started out when I showed up here as a little bit of a side project. And last summer I wrote a research grant to A3 and it got funded. So with a little bit of money, it's kind of gained some traction recently. And so let's just get into it. Many of you guys might be familiar with a study done by Dr. Kevin Hammonds during his PhD, which was looking at the ice-snow interface under a temperature gradient. And so what he did was essentially make this snow structure where he had a snow layer, an ice lens, and then another snow layer, and then put it under a temperature gradient such that you'd expect to see outside, like the earth being the warm side, typically around 0 degrees for like a seasonal snowpack, and then the air being the cold side. So you have your heat flow and vapor flow coming from the bottom of the sample to the top. I think he coined this the ice sandwich. But as you can see, like putting it under the temperature gradient, the blue line there is the imposed temperature gradient of 100 C per meter. And what he was able to observe was this like pretty significant temperature gradient increase above and below that interface. And so it's nearly like 6 times the imposed temperature gradient below and then nearly 3 times above it. And so what this is like, kind of like, I'm gonna term one end of the snow stratigraphy like interface or spectrum rather. You have a really high density ice layer in there, and then you have a relatively low density snow, right? So it brings me to my research question. So how does subtle density changes in snow layers, such as those created by wind slabs or by wind, affect kinetic snow metamorphism? So this is kind of stepping back from that extreme end of the spectrum of ice and snow, and is it possible that other layers that have density changes have a similar effect? And then, is there a thermal contact resistance at the interface of snow layers such that an increased temperature gradient could exist across other interfaces? I'm going to touch on what this term thermal contact resistance is on the next slide. It's a heat transfer concept. And then finally, what are the implications to avalanche forecasting? So not to get too nerdy on you guys, this is just a simple heat transfer concept that I think is kind of important for this. So you have 2 materials. It could be, say 2 copper or aluminum rods, and they're like finely machined, and you touch them together, and you apply a heat source at one end, and you expect the heat to dissipate over the length of the rods, right? But you have some sort of resistance at that interface. You're not going to have 2 mating surfaces that perfectly touch. I mean, as finally as you make that machine cut, like you're going to have, even on the micro scale, some sort of air gaps in there. And so this Q is the heat flux or heat flow through the material. And at that interface, you're going to have heat that wants to flow through these contact points more so than the air gaps, just because they have higher thermal conductivity. And so if we take this concept and kind of apply it to snow, say you had some layer that came down a couple days ago and it goes through some changes while it's on the ground. And so that's like one kind of material property. And then you have another storm or wind slab that blows on top of it. These layers have, different properties essentially. So this is the case that I'm kind of creating in the lab, where I have a high density wind slab on top, and then a lower density kind of underlying layer on bottom, and then applying a temperature gradient similar to the previous experiments, where you have heat flow coming from the bottom and the cold side on the top. And so how I'm making these wind slabs is with a wind tunnel that we have housed in the Sub-Zero Research Lab. The test volume is nearly which is just this clear spot right here, is like 4 feet long nearly. It's about as big of a wind tunnel we can get in the cold lab. And so wind sucks air through here and blows the snow into this collection box here, which is mounted at the other end of the wind tunnel. And it's basically just a acrylic box, 6 by 6 by 6, with a fine mesh backing that allows air to blow through it, but fine enough to where particles are being, caught in the box. And so here's just a short video of what this looks like. It's kind of sped up quite a bit. As you can see, it kind of builds up in this like drifting formation in the box, as you kind of expect from a wind drift. And so in order for me to get this interface that I'm interested in, I'm just going to go back to this slide real quick. I kind of excavate out some of that wind slab, so I have a nice clean layer, and that's my wind slab layer. And then what I do is take a sieve, and to create my low density layer, I don't put it through the wind tunnel. I essentially just like sieve other snow on top of it, so I have a wind-blown layer and then a lower density layer on top. So what this sample looks like, it's pretty small, about 50 millimeters, and I have a wind-blown layer interface with a lower density layer below it. And then I put this little ice lens kind of on the copper cap at the bottom, so it acts as like an infinite vapor fetch as I apply the temperature gradient. Because if I didn't have that, I'd lose material here at the bottom, and I'd lose contact between that copper cap, so it's just a vapor source essentially. And then place that into what we call a temperature gradient apparatus and apply a temperature gradient. Essentially it's just temperature controlled plates, and on the warm end, which is the bottom, -3 degrees, and on the top is -9 degrees. You guys think that's like a substantial temperature gradient? And enough for kinetic snow metamorphism? Yeah, it's like 120 degrees C per meter, which is pretty significant. These things just take time in the lab, so we kind of, apply bigger temperature gradient just to make the evolution of the interface happen faster. Maybe in the future, just kind of dial that back a little bit, but these are just to get some preliminary results. So once it's under a temperature gradient, pop it into the micro CT kind of once a day and just look at the evolution of this interface over time. At 0 hours, you can kind of see that interface there right in the middle, and you see it evolve over time. And after nearly 5 days, you have this these big grains growing out the interface, which would suggest that maybe there's a higher temperature gradient there. I haven't measured it yet. It's kind of just some preliminary results. And then using the micro CT, you can pull out like all kinds of numbers. These are just 2 graphs that I think are pretty intuitive to look at. This is the porosity versus the height of the sample. Looking at the interface, the red line is the initial condition. You have this little blip of kind of higher density or higher porosity zone at the interface. And then I think kind of stands out that this higher porosity zone over the 5 days kind of expands over the sample. So basically the interface is the low porosity zone, or rather the high porosity zone at the interface is kind of growing over time. And then looking at specific surface area, which is essentially looking at like individual like grains, the surface area of a grain over the volume of the grain. And like fresh snow or like dendritic crystals have a pretty high SSA. And then as they age over time or go through kinetic snow metamorphism, they have a reduction in SSA. And so it's just kind of interesting that at that interface, there's a drastic change in SSA. Another tool that we have in the lab that I use to characterize these snow layers is the snow micropen. And essentially, if you guys are familiar with it, it's just a probe that measures penetration resistance. And so this is what it looks like, and that's like the probe tip. And so this is just 2 probes into the same sample. You have your air signal here, which is essentially 0 force. And then it enters the low density snow that's just been sieved, not blown through the wind tunnel. And then it enters the wind blown layer. And just by blowing snow through the wind tunnel versus sieving it, there's nearly a 40% increase in penetration resistance just across those 2 layers. So measuring the temperature gradient at that interface is something that's kind of the next step in this project. What Kevin did for his, what Kevin used for his experiments was this micro thermocouples, where he essentially drilled these like tiny little holes in the side of the polycarbonate tube and stuck these thermocouple wires into the sample and was able to measure that temperature gradient. What I'm going to call like the next generation of temperature sensing is these microfabricated temperature sensors. Dr. Warnott, who is one of the kind of new professors in mechanical engineering that Kevin showed earlier, he's fabricating these temperature sensors on such a fine scale that like this right here is 8 measurements in, I'm actually going to zoom into it. So that whole piece is 2.5 centimeters, but you zoom into it and there's 8 measurements there over 0.5 millimeter. So these are essentially like thermistors. If you're familiar with what thermistors are, it's basically getting a temperature reading based on resistance. And so I think this scale is way too small for snow. This is like even below a single grain. But he's working on fabricating me one of these sensors to integrate into a sample holder to where it's more conducive to my experiments. I'm thinking something like 100 micrometer spacing across the array to get a pretty good measurement. And then this is just something that we have the capability of doing in our lab. I haven't done it yet, and this is not my work. I'll preface by saying that. But using a high-speed camera just to record drifting snow. This was done outside, but I'd like to do this using the wind tunnel. And then you can take this high-speed image and you plop it into a fancy engineering program and you do what's called particle tracking velocimetry, where you can track each individual particle. And so in this study, they were interested in blowing snow dynamics. And each one of these arrows is a velocity vector of like the blowing snow. What I would be interested in more so is just tracking like particles as they come into the wind tunnel and how the shape of them changes and maybe mass reduction before it gets deposited at the other end. And so just in summary, aside from the ice-snow interface, are there other snow layer interfaces where a micro super temperature gradient may exist? So the ice-snow interface being one end of the spectrum, wind slabs being one. I think another interesting layer to look at would be buried surface ore. And then lastly, understanding the thermophysical properties across snow interfaces may increase the avalanche practitioner's understanding of the development of weak layers. I know nothing that happens like at a micro scale is going to change how you guys forecast avalanches or move in the backcountry, but I think just having a good understanding of the underlying principles could add some intuition. So that's all I got for you guys. Thanks.